Okay. What? It's called a legato romagnolo. They're like a breed that's for hunting truffles. So yeah, he's like a water dog with like thick, sort of almost corded fur, and he's funny. Yeah. Anybody have any homework questions for that Deform? Okay. Well, quiz is going to be a week from today. And again, remember these are always cumulative, so you want to go back and look through from the beginning. So last time we talked about elongation or contraction due to internal tension or compression. There's another thing that can cause elongation, and that's changes in temperature. And so I'm sort of lumping these two in to the same category. So elongation due to temperature change. And mathematically, this one's a little simpler. The math isn't too complicated for any of this, but I'm going to call it delta sub T for thermal. So the change in length due to thermal changes. And this is equal to this alpha, which is a coefficient of thermal expansion, times the length, times the change in temperature. This alpha is called the coefficient of thermal expansion, and you can just look that up for a given material. You can always figure out the units of any parameter from the equation that it's used in. In this case, that you can think of this as like meters is equal to alpha times meters times degrees Celsius. And so alpha, those two cancel, and you just get alpha is equal to 1 over degrees Celsius. That's something you can just Google for whatever material you have. What this says is if the temperature increases, you get elongation. And if the temperature decreases, you get shrinkage, contraction. And one thing to keep in mind is this is valid for any length measurement. So if you start out with a torus-shaped thing, and you increase the temperature, you might, you can sort of talk yourself into all sorts of thoughts about what's going to happen for different measurements. Like say you increase the temperature of this, this donut shape, you might start thinking like, oh, well, it's gonna grow this way, but it's gonna grow in this way, and then that hole is gonna shrink, But every dimension is gonna increase. And so this is a measurement you could take, and that means that taking that measurement, you'd get an increase. Okay. All right, so let's do an example where we combine these two things. If you want to calculate the total elongation or total contraction, all you do is calculate it for the loads, for the internal tension, calculate it for the thermal expansion, and then just add those two answers together because we're talking about small deformations, so superposition works fine. You can calculate it like it's independent and just add them together. Okay, when you get big deformations, you can't do that anymore, but we're not doing that in this class. Okay. Okay, so let's say we have a shape like this. And this is 0.4 meters. This is 0.3 meters. And we're going to apply a force at this shoulder of 5,000 newtons and an 8,000 Newton force at the end. The cross-sectional areas for this part, the area is 0.01 meters squared. And for this one, the area is 0.003 meters squared. And the temperature increases 100 degrees Celsius. And we're going to assume that this is copper. And so we have a Young's modulus of 110 times 10 to the 9th pascals. The Poisson's ratio doesn't come into any of this calculation. And the coefficient of thermal expansion is 1 times 10 to the minus 5, 1 over degrees Celsius. Okay, so first let's do this for internal tension. If that's a free body diagram of the whole thing, we have a 5,000 Newton force here, 8,000 here. We have some reaction force here. And Newton's second law in the x direction says R plus 5,000 plus 8,000 is equal to 0. So R is negative 13,000 newtons. And we knew that from looking at it, that R, I drew that R backwards, but I think it helps just to keep yourself sane, to to just treat those reactions always in the positive axis directions. That's what I think. Okay, so now we can do our cuts. How many cuts do we have to do? Yeah, 2 cuts. So cut 1 is for that first 0.4 meters. So we have a 13,000 Newton force that way, the reaction load. And then we have our internal tension. So negative 13,000 plus T is equal to 0, so T is equal to 13,000. And again, that you could probably just eyeball and see that. And then cut 2 is for x's between 0.4 and 0.7. You have the 13,000 here, the 5,000 here, and the internal tension. So Newton's second law says negative 13,000 plus 5,000 plus T is equal to 0. So the internal tension is positive 8,000. Yep.
How is that 5,000 force applied? Is it like on the edge of it?
Yeah, it's applied somehow like around the, I didn't really think through what this represents or anything, but somehow it's applied on that shoulder.
Okay. Would there be a moment then?
Yeah, I guess probably this would be applied symmetrically. I mean, unless you're right that if it was only applied at one point like that, you'd have to worry about bending. Yep. But we don't know how to do that yet, so let's imagine that it's applied symmetrically.
Cool.
Okay, and notice you can make sense out of all these values. I mean, this 8,000 you also could have eyeballed by just imagining taking a cut from this side, taking a cut going the other way. You can see it's obviously in tension of 8,000 newtons. But there's no reason to be too smart with it. Just go through the steps, you know. You'll always have time to do it carefully. All right, and so now the elongation due to tension is TL over EA on the first piece plus TL over EA on the second piece. And so that's 13,000 times 0.4 divided by 110 gigapascals times the cross-sectional area of that first piece plus 8,000 times the length of the second piece divided by 110 times 10 to the 9th times 0.003. And what I got before is 1.2 times 10 to the minus fifth meters. Okay? And now we'll do the thermal expansion part. The thermal expansion part, you don't have to break anything up, no matter what the geometry is. In every length dimension, it just elongates or contracts according to this formula. So the elongation due to thermal expansion is this. So we were given 1 times 10 to the minus 5 as the coefficient of thermal expansion. The total length is 0.7. The temperature increases 100 degrees, so this delta T is positive. And so you get a value of 7.0 times 10 to the minus 4 meters. Or 70 times 10 to the minus 5. And so the total elongation is just the sum of these two. Or 71.2 times 10 to the minus 5 meters. Any questions about that?
So I think you went over this, but the L for the thermal, that could be the length in any dimension, any direction.
Yeah.
And you can get the...
That's right.
expansion.
Exactly.
Okay.
That's exactly right. That'll tell you the change in length of any length measurement you want. So for thermal expansion, you can use that formula, not the one for tension, but the one for thermal expansion. You can use that for any length measurement you want. So if you wanted to calculate the change in the perimeter, the L you put into that formula could be the starting perimeter of the thing, and it'll give you the right change in perimeter length.
Measure from any 2 points.
Yeah. But it only works for thermal, it doesn't work for the other things.
Okay.
So if you measured some wavy length, it would give you the change in that wavy length after the expansion.
So it doesn't have to be linear?
Right. Right. But if you're gonna add it to other stuff, it has to be linear.
Okay, that makes sense.
So, technically speaking,
I like where this is going.
which you have to get the thermal expansion, which you have to add the length of the tension to the thermal expansion, because it got a little bit longer and then you thermally expanded it.
Well, that's where superposition comes in. That's a good question. And really that question comes up in everything we do in this class. And if you start getting into big deformations, you have to worry about what matters isn't the starting length. What matters is the current length, and it makes things very complicated. But since everything we're doing is small deformations, we can use original lengths for all that stuff. But yeah, thank you for filling in for Joy. That's like a question Joy would ask, I feel like. And someone has to do it.
So, what if you thermally expanded it first and then stretched it, which you have to find?
Well, the answer is that as long as the deformations are small, those answers are the same for all practical purposes. You know what I mean? Like if you put in, how much would it change this answer if I put in, instead of a length of 0.4, I put in a length of 0.4007
Yeah.
or whatever. You know what I mean?
So there's two.
Yay. She missed it. You summoned her. Okay, so now the cool use of this, in my opinion. So now we're going to use this for statically indeterminate structures. Well, we can't do much for structures with only, tension and compression, but
And that was the other question I had. This works for compression because it's the deformation they're swallowing as well. Like buckling and things like that on the
yeah, you sort of have to think independently about whether buckling is going to be an issue. And I guess we can talk about that more later when we start talking about column buckling. But yeah, if the length is big compared to the width, then little by little, buckling becomes more of an issue. And yeah, you're right about that, but we can't say much about it yet. Yep.
So are we ever gonna deal with something where like the change in temperature would affect the metals or
Right.
the E? I don't remember the.
No, we're not going to.
Okay.
Yep. This is as far as we're going with thermal stuff. Okay, so now we're going to apply this to statically indeterminate structures. Statically. And I don't know, I always like the points where we come to like, okay, we hit this roadblock before. Maybe we didn't talk about it so much, but the last time you saw this stuff, we hit a stopping point and we can't do any more. Well, now we're going to get past a stopping point that we had before. So now we're going to start with a problem where we're going to start on all these statically indeterminate structure problems. You start by doing the statics. You sort of assume like, you don't know going into it that it's statically indeterminate. You do the statics, and only then do you say, like, I can't solve this using statics. But then we use other stuff to get around what used to be a roadblock for us. So I'm going to give you steps. It's just 2 simple steps. And then we'll do an example. So the first step is do the statics. And when you do that, you get all the useful equations you can from Newton's laws. In statics, once you got all the useful equations you could from Newton's laws, then you had a system you could solve. But in this case, what you see is you have more variables than equations. Well, we're doing this in dynamics right now too. So like, what do you do when you have more variables than equations? You look for constraint equations, other relationships between the variables you've already defined that come from geometry or whatever. And so now you use the elongation equations. to define the needed geometric constraints. Let's say geometric constraint equations. And that's just always going to be the steps that you take on all of these statically indeterminate problems. You come up with a number of equations and a number of variables. You can't solve it. That's how you know it's statically indeterminate. And then you use the macroscopic change equations to give you your geometric constraints. So here's an example. So let's say you have a fixed floor and ceiling, and a column between them. And the cross-sectional area of that column is 0.01. And a force is applied. Let's say this distance is 3/4 of a meter. And this is 1/4 of a meter. And you apply this downward force of 20,000 newtons at that location. And we want to know what are the reactions at the floor and the ceiling. Okay, so first I'm going to do the statics. So we have a reaction force here, I'll call that RA. And a reaction force here, I'll call RB. Notice I'm not trying to guess what the directions of those forces are. I'm just putting them in the coordinate system axis directions. The signs will come out on their own. And then down here, we have the 20,000 Newton force. Newton's second law in the y direction says RA plus RB minus 20,000 is equal to 0. Okay. Now this is the first time that we need to recognize that this is statically indeterminate. I mean, you can't solve one variable for two equations. You can't solve one equation for two variables, I mean. So this is statically indeterminate. So now what we're going to do is come up with an expression for the elongation of this column. And the total elongation of it, since it's in between these two fixed, it doesn't have any room to grow in there. So the total elongation has to add up to 0. Okay? Is everybody with me on that? The fact that the floor and ceiling are fixed means that when we come up with an expression for the elongation, it's going to have to add up to 0. So, okay, let's come up with the total elongation. We have to think about it a little more than that. So I'm going to do it in cuts. And I'm going to go like, I'm going to think of it flat, where x goes from 0 to 0.25 meters. We have our RA like this. We haven't made it to the 20,000 Newton force yet, so now we just have an internal tension. Newton's second law in, I guess, what's now the x direction says RA plus T is equal to 0, so T is equal to negative RA. Okay. All I'm doing is just calculating those internal tensions right now, so we can use them in that elongation formula. And our second cut is for x's from 0.25 to 1. We have our RA. We have our 20,000 newtons here. We haven't made it to the top connection to the ceiling yet, so we have our internal tension. And so RA minus 20,000 plus T is equal to 0. So the internal tension on this part, T, is equal to 20,000 minus RA. Since it's statically indeterminate, we can't come up with internal tensions as numbers. They have to include variables because we don't know what those are. Okay. Anybody have any questions about what I'm doing yet? Now, these are the internal tensions we're going to use in the elongation formula. So the total elongation is equal to the elongation on that first quarter of a meter, the lower quarter of a meter, plus the elongation on the higher 3/4 of a meter. So this is negative RA times the length of that section, 0.25, divided by, well, I didn't give a Young's modulus. It turns out it's not going to matter here. You'll see. I'm just going to put this in as E. But if I gave you that it was steel or copper or whatever, you would put that in there. And the cross-sectional area is 0.01. That's not going to come into it either. That's the elongation for the bottom quarter. Now we're doing the top 3/4. So the internal tension times the length divided by Young's modulus times the cross-sectional area. And all this is equal to 0. And this is just because it has to fit between the floor and ceiling. Okay. Multiply both sides by this common denominator, and those go away. And so now we just have negative 0.25 RA plus 15,000 minus 0.75 RA is equal to 0. And so RA is equal to 15,000. And now, so that is the reaction load at the floor. What about at the ceiling? Well, we have this equation. These two have to add up to 20,000. You know, you can think of this as our first equation. This is our second equation. And so RB is equal to 5,000. And so if you redraw this free body diagram, you have an upward force here of 15,000. The downward force here of 20,000. And then this is an upward force of 5,000. Yep.
Would you be able to kind of work backwards like that? Like, kind of, I guess similar to the problem here where it's like you have 0 meters to move. Could you be like, oh, you have this much space to move, what's the maximum force?
Yeah, yep. Or you could have things where something, you know, you have a certain amount that this is stretched. Yeah, I mean, I guess it's sort of what you're saying, like, say it's stretched 5 microns or whatever, what loads are those going to introduce? Okay, let's do this problem again, but include some thermal stuff. Okay, so you can see how that all goes together. So this time, let's say, this time we do have to know the Young's modulus. So let's use, we had those values for copper before, let's use those again. So 110 times 10 to the 9th pascals. And the coefficient of thermal expansion is 1 times 10 to the minus 5, 1 over degrees Celsius. And let's say that the temperature is decreased 50 degrees Celsius. Yeah, it got colder. You know, getting colder causes contraction. So if you make this colder, forget about the 20,000 for now. That's in order for the floor and ceiling to hold onto this bar as it's trying to shrink, it's going to have to be in tension on both sides. Okay, you see that?
The floor and ceiling are going
What?
the floor and ceiling are going to provide a tension.
Yeah. Otherwise, I mean, if they don't provide that tension, that's just going to break free of those and shrink. It wants to shrink, you know?
So imagine it's connected.
It's like welded to the
Yeah.
ceiling. So,
The lowered temperature is going to make that bar want to shrink. The only thing keeping it from shrinking is the connection to the floor and ceiling.
We still have that 20,000 Newton force though.
Yeah, we'll see what happens with that. I don't have the answer in front of me, so we'll see.
I see. So,
But if you took that away,
gotcha.
I'm just trying to give you intuition about what would happen there. Okay, so we'll start with the statics again. And the statics look exactly the same as they did before. We have an RA here, 20,000. RB. Newton's second law, just looking at the vertical, says RA plus RB is equal to 20,000. And so again, this is where you see that it's statically indeterminate. And so now we do the cuts. And all this still looks the same. So for x from 0 to 0.25, we have this force RA, the internal tension T, and so T is equal to negative RA. So far, everything still looks like it did in the first example. Our second cut is still going to look like the first example. So now we have RA, 20,000 Newton force, and the internal tension. So the internal tension is equal to 20,000 minus RA.
That should be 0.25 to 1, right?
What?
For x.
To 1, yeah, thank you. Yeah, so far everything looks exactly the same as it did in the first example. And now we'll calculate the change in length due to internal tension. This is going to look exactly the same as what we had before. So we have negative RA times the length of 0.25. This time we would have seen that we couldn't do this problem without knowing Young's modulus, so we'll put that in the cross-sectional area. Plus the elongation of the top piece. So 20,000 minus RA times 0.75 over 110 times 10 to the 9th times 0.01. But now with the temperature change, this isn't the only thing causing a change in length. We also have the thermal change. So that's the coefficient of thermal expansion times the length times the change in temperature. And so we get negative 5.0 times 10 to the minus 4, I think, right? And so now the total elongation is negative RA times 0.25 over, I'll combine these, 110 times 10 to the 7 plus 20,000 minus RA times 0.75 divided by 110 times 10 to the 7. plus negative 5.0 times 10 to the minus 4. And since it's attached to the floor and the ceiling again, this has to be equal to 0. Okay? And so now we have negative RA times 0.25 over 110 times 10 to the 7 plus 20,000 minus RA times 0.75 divided by 110 times 10 to the 7 is equal to 5 times 10 to the minus 4. And so I'll multiply both sides by 110 times 10 to the 7. And so you get this is equal to 550,000 and so negative RA is equal to 535,000, right? And so that's a huge force. So RA is equal to negative 535,000 newtons. Well, RA, from our first equation, RA plus RB has to be equal to 20,000. So negative 535,000 plus RB is equal to 20,000. So RB is equal to 555,000 newtons. And so what you get here is for RA, we got a negative. For RB, we got a positive. And there you go. What's that stress going to be? The cross-sectional area is 0.01 meters squared. So that would be like 55.5 megapascals, you know, on the top half. So that's quite a bit. Any questions about that? Okay, well, I mean, that's those, like with internal tension and thermal stuff, these changes in length, these displacements the math is pretty easy, but this is fundamentally the way we're going to approach all of these problems. The math is just going to get more complicated when we get into deflection due to bending and stuff like that.
Yeah.
Any questions? Yeah.
I mean, that's a pretty large force for just, I mean, sure.
Yeah.
Temperature got pretty cold, but
Right.
I mean, is that just because it's made out of a material that has high?
It's a strong material, and that's not, I don't think, a particularly high coefficient of thermal expansion or anything. I just think you have a very stiff material. You know, the flimsier the material is, like if a material doesn't have a high Young's modulus, then the temperature says, I want to contract this much, and the material's like, sure, no, it's no big deal to me, you know?
Yeah.
But if you have like a metal like this with a big area, it fights pretty hard against that.
Yeah, I guess in the real world, I guess you have some deformation or whatever attaching to that would,
Mm-hmm.
but if,
That's right.
so I guess if there's two pieces that did not deflect at
Right.
all, that would.
Yeah, that's right. Yep.
What are the chances that this would just shatter in the real world from 535,000?
I guess that all just depends on the specifics, but I think the answer is 100% in this case.
Well, I would probably just stretch and it would shatter.
It depends what the material is.
Crack, so it would just.
It's also being
Yeah.
cooled 50 degrees Celsius, which means its brittleness is probably going to rise. And worse and
Yeah.
things tend to like to change.
That's true. I don't know, 50 degrees. I don't really have a feel for how much that changes the behavior of a metal.
That's fair. I guess I was thinking.
About the delta T, like what is that measured relative to?
Just whatever it starts. So it's saying that it went down 50 degrees from what the temperature was when there was zero load on that.
Okay.
Yeah, when it fit in exactly
It started
perfectly.
like really hot or really cold, but then it shrunk even more.
Yeah.
Because it got colder.
Uh-huh. Yeah. It's just compared to zero load.
So for the temperature though, I would imagine that if